You're about to participate in a review of GM's Computer Command Control, or C3, engine control system. The first engine control system designed to be used by almost all of GM's different engine groups. Its development was the evolution of many different spark control designs produced during the mid and late 70s. Unlike its predecessors controlling only spark, C3 in most applications is designed as a full-function system controlling fuel ratio and spark advance along with a host of additional engine functions. The C3's primary design function is to improve mileage and emissions without sacrificing drivability, which is the problem of earlier spark control designs. The C3 ECM is found in two common engine control designs, the full-function C3 and the later C3P4 ECM. The full-function C3 system is used with both feedback carburetor and throttle body fuel injection. The C3P4 produced later is a faster version used in throttle body fuel injection applications. There are variations to the C3 systems, including the Mini-T, a limited application fuel control design found on early economy cars, the 82 and 83 Ols LC variation, and the late model GM30 integrated ECM-BCM configuration. All of these designs are different, but on the whole operate and diagnose using procedures similar to those covered in this video. The ECM, the heart of the GM C3 system, can usually be found in the passenger compartment. For exact locations, consult a component locator guide. The ECM has two parts: the ECM itself, which is replaceable, and the programmable read-only memory chip called a PROM. The PROM tailors the ECM to an exact application. The ECM is powered by fused battery voltage. When the ECM is powered, it supplies a regulated 5 volts, or reference voltage, to its sensors. The ECM monitors returning sensor signals and compares these signals to its PROM information in order to determine engine operating requirements. The ECM provides ground to individual 12-volt powered under-the-hood solenoids based on both the PROM and sensor information. The C3P4 ECM, a later more advanced computer control unit, takes the engine management assignment a step further with the addition of a calibration assembly called a CalPack. CalPack information provides smoother engine operation under a wider variety of conditions. The next development in processors is consolidation of the PROM with CalPack into a single case assembly. This unit is called a MEMCal. The GM C3 system was first introduced with a driver warning lamp called a check engine light. This lamp was changed on all later models to read "Service Engine Soon." The ECM lights the lamp after being alerted to a problem in the system by the sensor. The lamp remains on until the problem is fixed. The ECM controls the service engine light in 80 and 81 applications. An electronic relay, also called a lamp driver, is found on later versions. The lamp driver illuminates the service engine soon light even if there is a complete ECM failure. The check engine lamp is one of the technician's primary diagnostic tools. The check engine lamp provides output from the ECM's extensive self-diagnosis application. A jumper wire plugged into the assembly line diagnostic connector, the ALDL, allows codes to be extracted on C3-equipped vehicles. A series of codes is stored in the ECM's short-term memory when there are problems in the system. These trouble codes can be recalled over a period of as many as 20 restarts, or until battery voltage is lost, whichever comes first. The ALDL connector is a block of 5 female spades set up in a common N-line connector, like that found in 80 and 81 models. A standardized 12-pin connector is found on 82 and later applications. The jumper is connected between pins A and B. The upper right-hand pins trigger code retrieval. On earlier applications, a single male spade is inserted between the open terminal divider on the last 2 pins to initiate ECM code retrieval. Both techniques accomplish the same thing, taking a lead from the ECM to a known good ECM ground. Turning the key on after grounding almost all C3 versions allows the system's ECM to transmit stored trouble or fault codes. The stored trouble codes are displayed as a series of 1 to 2 second flashes. Codes flash 3 times in sets of 3, beginning with stored code 12, and continue upward until the last one is displayed. A code 12 should always be present when the engine is not running. If a code 12 is not being displayed, the tech proceeds to the No Code 12 diagnostic procedure, which will determine if there is an ECM or PROM problem. All other codes are considered suspect until it can be determined why the ECM is failing to recognize the absence of a TAC reference. When it is not possible to get trouble codes to flash, go to the No Codes diagnostic chart and the lamp driver diagnostic procedures prior to any further repairs being attempted. Codes, after being recorded, should be removed from the system in order to find out if either an actual system problem exists or if there are intermittent faults being set by poor connections or outside tampering. To erase stored codes, remove the ECM's battery voltage by pulling the ECM fuse for approximately 10 seconds, then replace. The separate ECM ground connector found on later models can be disconnected at the battery. Codes are also erased by pulling either battery cable for about 20 seconds. When the codes have been cleared, the car is driven to check if the codes will reset. If after driving the codes are not reset, they should be considered intermittent. The system is then checked for either poor or corroded connections. If the codes reset, start with the lowest and follow the appropriate diagnostic procedure to figure out the problem. The codes are then cleared and the vehicle driven after each fault is repaired. Both carbureted and fuel-injected applications function the same with the key on and engine off. They differ when the ALDL is jumped with the engine running. Carbureted applications will transmit fault codes but not a code 12 unless there is a TAC reference problem. A code 12 is the only code which will not set in memory. C3 engine operation changes when the ALDL jumper is connected with the engine running. This puts the ECM into field service mode. Carbureted applications in field service mode have less accurate fuel control, bypassing of any delay timers, fixed timing advance, and a loss of many related emission control functions. Basic idle in field service mode is usually acceptable, but the vehicle should not be run in this mode for any extended period of time. Fuel-injected models exhibit an even more profound change when the ALDL is grounded while running. Idle increases immediately, timing becomes fixed, emission controls are defaulted, and the check engine lamp begins to flash depending on the engine's fuel condition. The check engine lamp will flash on when the engine is warmed up and the engine is running rich. The lamp goes out when the engine runs lean. Cold engines will flash on and off at regular rate until the engine is warmed up. Other lamp flash sequences indicate trouble in the system. The monitoring of fuel ratio on fuel-injected vehicles in field service mode is used to determine a lazy or damaged fuel delivery system. If the fuel delivery system is operating correctly, the check engine lamp will flash on and off every 2 to 3 seconds. This indicates that the ECM is constantly correcting minor differences in fuel delivery. Now let's take a closer look at the C3 system's components. The C3 systems depend on 5 primary signals to determine the necessary control of fuel and timing. They are the HEI reference, manifold absolute pressure sensor, throttle position sensor, coolant temperature sensor, and the exhaust oxygen sensor signals. The C3 system's ECM uses additional sensors depending on the application. Additional sensors include the baro sensor, the speed sensor, the idle tracking sensor, the brake sensor, and the park neutral switches. There are others. Be sure and consult the appropriate service manual for the complete list and locations of sensors, switches, and actuators. The first input we're going to look at is the HEI TAC reference. The C3 distributor is based on and is very similar to the early HEI distributor. Both systems use a magnetic pickup to provide the trigger signal. The trigger signal is an AC signal and is generated by the magnetic pickup. This AC signal has to be converted into a digital on-off signal before it can be used to control the ignition coil switching transistor. The conversion is done by the module, just like early HEI systems. Those early systems sent the signal directly to the switching transistor. The C3 module operates differently. It splits the signal. One branch of the trigger circuit goes to the ECM, where it becomes the HEI reference signal. The HEI reference signal exits the distributor and passes through a 4-pin connector before going on to the ECM, where it is used to determine engine speed and timing needs. The HEI reference signal is used also in fuel-injected applications to signal the ECM to trigger the injectors. Without this reference signal, fuel-injected engines will die. The other branch of the C3 module's trigger circuit goes to the switching transistor and is used to control coil firing. This branch of the trigger circuit gets to the switching transistor by passing through an electronic relay circuit. This relay circuit has a default mode called the module mode. The module mode directs the trigger signal to the switching transistor just as it did in the older 4-pin HEI module. This setup permits the ignition to provide spark even if the wiring's external leads are damaged. The module is now able to fire the coil and trigger the injectors for starting. When the engine is started, the ECM is ready to supply the necessary spark advance for optimum engine operation. The spark advance signal is based on incoming sensor and ECM pre-programmed data. This electronic spark timing signal is a duplication of the original HEI reference signal, with the exception that it has either been advanced or retarded as needed by the ECM. The EST signal returns to the module, passing through the same 4-pin connector, and continues on to the other side of the module's electronic relay. The trigger signal leaves the module on the HEI reference lead and returns to the module on the EST lead. The engine needs one more important signal to function properly. The module's electronic relay must be signaled to switch over and accept the EST signal from the ECM. In order for this to happen, the ECM, with the engine's RPM exceeding 200 to 400, sends a 5-volt signal to the module on the 3rd lead of the 4-pin connector. This is called the bypass signal. The bypass signal activates the electronic relay switch, which then switches over from the HEI reference lead to either the advanced or retarded EST signal. The last lead on the 4-pin connector is an additional ground, which ensures reliable operation. This HEI reference EST return type of timing control is found on all GM C3 systems, from the earliest C3 HEI to the latest DIS C3I system. Since the TAC reference is so important, the ECM contains several diagnostic codes for this circuit. Reference signal problems are indicated by either a code 12, a no TAC reference situation with the ALDL grounded as mentioned earlier, or by a code 41. A code 41 indicates that engine vacuum is available, but HEI reference pulses are not. A code is sometimes sent by either loose or corroded terminals at the 4-pin distributor connector. A code may also be set in memory during base timing adjustment. Trouble in the EST and bypass circuits are indicated by a code 42. The ECM monitors the EST lead, ensuring that a high-low signal, called a signal toggle, occurs under the proper conditions. During cranking, for example, the EST signal should be grounded in the module and should not be able to go high. If it does, a code 42 is set in memory. A bypass circuit going open pulls the EST signal to ground during engine operation, also setting a code 42. The technician then follows appropriate diagnostic procedures. A word of caution about code 42. Many C3 applications require that the 4-pin distributor connector be disconnected in order to check base timing. Disconnecting the connector will usually set a code 42 and sometimes even a code 41. Make sure all codes are cleared. Then check to see if they reset prior to performing diagnostics and repair. How much the EST return signal is advanced or retarded depends on three things: the calibration of the ECM, the permanent factory data stored in the PROM, and information coming in from other primary inputs, including manifold absolute pressure, throttle position, coolant temperature, and oxygen sensors. MAP sensor data is used by the ECM to monitor engine vacuum and to adjust timing and fuel. It takes the place of the old vacuum advance and power valve. MAP sensor circuit problems are identified with the code 32. GM has used two types of MAP sensors over the years: an absolute type, which compares engine vacuum with a sealed chamber, and a differential type, which is vented, allowing the engine vacuum to be compared to atmospheric pressure. Both sensors are powered by the ECM's 5-volt reference voltage. They return a signal voltage between 1/2 volt and 4 1/2 volts, depending upon the sensor type and amount of engine vacuum. Those applications using a sealed MAP sensor will employ also a baro sensor to monitor and report on atmospheric pressure. An open-to-the-atmosphere type baro sensor was moved to the passenger compartment in '85. Throttle position sensor designs vary depending either on carburetor or fuel injection application. The TPS is found mounted either in the float bowl on carbureted applications or on the throttle plate of fuel-injected systems. It's supplied with a 5-volt reference, signal return, and ground lead. The signal on the return lead starts at about 1/2 volt at idle and increases smoothly as the throttle is slowly opened. There will be a wide range of drivability problems if the TPS signal is erratic in any way. TPS problems are identified with a code 21. The coolant temperature sensor is mounted in the water jacket. Its data is used by the ECM to make fuel and timing corrections needed for cold engine operation. The original CTS had an unreliable barrel-type connector. The latest configurations have a black oblong DIN-type pin connector and include a replacement connector. CTS circuits display two types of problems: the code 14 circuit shorted and the code 15 circuit open. Central to the fuel control system is the oxygen sensor, which is mounted in the exhaust system. It monitors the oxygen content in exhaust gases, sending a minimum 1/10 volt signal to the ECM when the fuel mixture is lean and a maximum 1 volt signal when the fuel mixture is rich. The oxygen sensor voltage signal continually moves from high to low, crossing a 4500 volt reference voltage supplied by the ECM on the oxygen sensor line. The fluctuation is measured in what is called cross counts. These cross counts are used by the ECM for tailoring fuel mixture. The oxygen sensor will not produce voltage until it reaches 600 degrees Fahrenheit, 316 degrees Celsius. Based on these 5 primary inputs, the ECM controls ignition timing, emissions including the EGR and air pump control solenoids, diagnostics, and fuel control, our next area of study. This full-function carbureted engine measures 3.8 liters, 231 cubic inches, and is equipped with a feedback carburetor, as are all GM carbureted engines having a system computer. This system uses an electric mixture control solenoid. This solenoid operates a metering rod system in the float bowl. The metering rod supplements fuel that is supplied by the idle and main carburetor systems, which vary the air and fuel ratio to meet specifications. This control is accomplished by grounding the MC solenoid 10 times a second, and then changing the time the solenoid is grounded against when it is not grounded. We call this on-off type of control a duty cycle, or more commonly, dwell. When the MC solenoid is grounded, the metering rod is pulled down. This shuts off the fuel and leans out the engine. When the MC solenoid is not grounded, the metering rod is raised, which lets more fuel in, creating a rich mixture. When the duty cycle or dwell is changed, the ECM provides optimum fuel delivery rate for any need. The dwell of the MC solenoid should be, ideally, 30 degrees with the dwell meter set to the 6-cylinder scale. The other type of fuel control used with the C3 system is throttle body fuel injection. Throttle body fuel-injected models have an in-tank electric fuel pump, which provides fuel to the injectors through an inline filter. The pump supplies fuel pressure in excess of the vehicle requirements. Situated in the intake manifold-mounted throttle body housing is an electrically pulsed injector, which makes up the throttle body injection system. Injector on time is controlled by the electronic control module, which regulates fuel to the engine. The throttle body fuel injection is available on 4, 6, and 8-cylinder applications. Now, let's review how to diagnose the C3 system. Computerized engine control systems are easily diagnosed using onboard diagnostics and with the use of a selection of tools including a scan tester, a tachometer, a dwell meter, a digital multimeter with a minimum 10 megohm input impedance, a vacuum gauge, and fuel injector test light for both throttle body injection and port fuel injection. A test light rather than a voltmeter must be used when called for by the diagnostic chart. Servicing computer-managed vehicle engine systems involves eliminating all possible causes besides the computer first. If all the components check out, then the computer is tested. This is termed the decision tree method of system diagnosis. The components and systems which are tested in eliminating trouble prior to diagnosing the computer and its PROM are the sensors. They are checked to see if they open and close and if their resistance values are to specs. Solenoids are checked by applying voltage and taking a look at their operation. Measurable resistance should be found across the windings, and they should neither be shorted to ground nor open. Either a shorted or low-resistance solenoid can damage the computer. Check all solenoids before replacing the computer. Wiring diagrams having connection locations and resistance values are used to verify circuit condition. Next, the system circuits are checked by disconnecting wiring at both ends and measuring resistance to specs. If more than 5 ohms are measured, then wires need to be either cleaned or repaired. The ohm meter is then connected between one end of the wire and ground. Several 100,000 ohms resistance should be found. If not, the wire is considered shorted and has to be repaired. The key to diagnosing computer-managed vehicle systems is the elimination of fundamental sensor, solenoid, and wiring problems before considering the computer and PROM as a source of operating problems. Prior to any formal diagnosis being performed, the vehicle should be checked for poor electrical connections, damaged vacuum hoses, faulty high-tension ignition wires, and fuel and a functioning fuel supply. Troubleshooting these systems involves making sure that all engine systems not controlled by the computer are functioning properly. Do not continue testing unless all non-computer-related problems are corrected first. Doing a diagnostic circuit check, which verifies the reliability of the diagnostic system, and concluding with a system performance check for all carbureted models. On fuel-injected applications, the diagnostic circuit check is followed by a field service mode check. The diagnostic circuit check for full-service carbureted models determines if the service engine soon light works, and that the ECM is operating and able to recognize stored fault codes indicating problems. If there are no codes, then the system performance check is executed. The diagnostic circuit check is a 3-step procedure, including checking the operation of the service engine soon light. This is a key-on, key-off type of test. The second step is the grounding of the test terminal to determine if there are trouble codes stored, or connecting a scan tool for the extracting of codes. The third step gives the choice of servicing codes or going on to the system performance check if no codes are present. The system performance check for full-service carbureted models verifies that the ECM system is operating to specs. It is a 3-step decision tree that includes a carburetor air-fuel mixture check, closed-loop operation, use of a dwell meter, and a switching valve solenoid check. Hard codes trip the service engine soon light to burn continuously when the engine is running. Diagnostic charts will usually not help to analyze intermittent codes. Here's how to distinguish between hard and intermittent codes. Enter the diagnostic mode manually. Read and record all the stored trouble codes you find. Exit the diagnostic mode and clear the trouble codes. Turn the ignition switch to off. Remove the ECM fuse from the fuse block for 10 seconds, then put it back. The trouble codes should now be cleared. Now that you have a list of the codes, apply the parking brake and put the transmission in neutral or park. Block the wheels and then start the engine. The service engine soon light should go out. Let the warm engine run for 2 minutes and check the service engine soon light. If the light comes on, enter the diagnostic mode manually, reading and recording the trouble codes. What you will be getting will be hard failure codes. If you had previously recorded stored codes 13, 15, 24, 44, 45, and 55, you may need to road test the vehicle in order to reset the hard failure after clearing the trouble codes. If you don't get a service engine soon light, all the stored trouble codes are probably intermittent failures. Now, when the light comes on but doesn't stay on, there may or may not be a trouble code stored. You've got an intermittent problem. Here's what to do to trace the problem source of an intermittent service light. Carefully examine connectors and terminals, making sure there are good wire-to-terminal connections and that they are clean. If you have any doubts, chemical cleaning is always a sound procedure. Carefully examine the secondary ignition system for either secondary leakage or excessive resistance as possible sources of intermittent fault codes. There may be an intermittent short to ground of the wire from the warning light to the ECM. Either the ALDL test terminal may be shorted to ground, or there may be poor ECM ground terminal connections. Either will cause a check engine lamp to illuminate without storing codes in memory. Now, let's take a look at a specific trouble code and some related circuit tests, which will give us an overview of what it means to go through a trouble code's decision tree. This engine has given us a code 21. This indicates a TPS circuit problem. Using the GM diagnostic chart and following the outlined decision tree, we can quickly zero in on the specific component that requires service steps. Using a scan tool, we'll determine if the voltage is over 2.5 volts with the throttle closed. Generally, we see about half a volt on most GM applications. A code 21 will set if there is more than 4.5 TPS volts, either with the ignition on or the engine running, or if there is a high TPS voltage, or if there is a low airflow. A condition must have existed for a time period of from 3 to 10 seconds to set the code. If the TPS does not play in excess of 2.5 volts, the code 21 is considered intermittent. This may be caused either by terminal damage or a dead spot in the TPS. If the TPS does display in excess of 2.5 volts, then disconnect the sensor. The multimeter should now show less than 0.2 of a volt. If it doesn't, either circuit 417 is shorted to voltage or the ECM is bad. If there is less than 0.2 of a volt, then probe the sensor's ground circuit with a test light that's connected to battery voltage. If the light stays off, there is either an open sensor ground circuit or a bad ECM. If the light comes on, there is either a faulty connection or the sensor is bad. All codes should now be cleared and closed-loop operation confirmed. The service engine soon light should not be illuminated. Now, if there is a drivability problem but no code has been set, the system performance test is then used for diagnosis. The system performance check for full-function carbureted models verifies that the ECM system is operating to specs. It is a 3-step decision tree that includes a carburetor air-fuel mixture check, closed-loop operation, use of a dwell meter, and a switching valve solenoid check. The first step of the system performance check for full-function carbureted engines involves starting the engine, grounding the test terminal only while the engine is running, connecting a tachometer, and disconnecting the mixture control solenoid and grounding the solenoid's dwell terminal. The engine is then run at 3,000 RPM. The engine is kept at this RPM and the solenoid is reconnected. The mixture control solenoid's dwell ground terminal is removed before going back to idle. You're given two choices at this stage. If there is a drop of less than 300 RPM, or there is an increase in the RPM, the MC solenoid connector, as viewed from the end with the solenoid connected, is checked for proper attachment. The evaporator and canister are then checked for fuel loading. Purge valves, bowl vents, and fuel in the crankcase is checked out as possible causes of RPM drop or increase. If these check out okay, then the carburetor or MC solenoid is probably at fault. A dwell reading on C3 carbureted models indicates if the mixture control solenoid is working and if the fuel mixture is rich or lean. The dwell meter is set on the 6-cylinder scale, no matter the number of engine cylinders. Connect the dwell meter to the green connector you'll find near the carburetor. The connector will not be connected to any circuit except when testing with the dwell meter. Keep the terminal wire away from all grounding sources, including rubber hoses. Dwell should be fixed between 10 and 50 degrees prior to the engine getting up to operating temperature, which signals that the system is in open-loop operation. The dwell meter should, with the engine idling, and to operating temperature specs, vary between 10 and 50 degrees. The carburetor is set on the high step of the fast idle cam and run for a minute or until the dwell starts to vary, whichever happens first. The engine is returned back to idle and the dwell noted. At this stage, there are 4 possibilities. The dwell will vary. It will be fixed from 10 to 50 degrees. It will be fixed under 10 degrees. Or it will be fixed at 50 degrees or over. In any one of these choices, you'll be directed to diagnostic chart testing or to go on to Step 3. Step 3 directs you to check the dwell at 3,000 RPM. There are 3 possibilities. Dwell will be 50 degrees or over, in which case you're instructed by the service manual's decision tree to service the carburetor, including its adjustment. A faulty canister purge may also cause this condition. Another possibility. Dwell will be under 10 degrees. You're directed then to check for a leaking air switch valve to the exhaust ports at 3,000 RPM. If no leaking is found, then you're instructed to service the carburetor, including its adjustment. This could also indicate a vacuum leak. Finally, the dwell might fall between 10 and 50 degrees. This signals normal closed-loop operation and requires you to check the air management system. If there is no trouble in the system, long-term memory is cleared and you're directed to check out drivability symptoms. The field service mode check, designed for fuel-injected models, involves grounding the ALDL while the engine is running. Remember to engage the parking brake and block the drive wheel because the parking brake on front-wheel drive models will not hold the drive wheels. The check engine lamp will indicate operational modes with the ALDL grounded and the engine running. The light will flash at 2.5 flashes per second to indicate proper open-loop mode. The closed-loop mode will be indicated if the service engine warning light flashes at a rate of 1 per second. A lean exhaust is indicated if the light is off most of the time during this sequence, and rich if it is on for the majority of the time. The field service mode check for fuel-injected vehicles confirms that the fuel system and closed-loop mode is operating properly. The oxygen sensor on some engines cools off in a short time with engine idling, sending the engine into open loop. To get back to the closed-loop mode, the engine is run at part throttle for a few minutes, accelerating from idle to part throttle several times. The field service mode check after clearing codes should be performed following any repair. Computerized engine control systems are diagnosed in this order. Make sure that all engine systems not associated to the computer are functioning to specs. Now don't continue testing unless all non-computer related problems you find are functioning or have been repaired if faulty. This concludes our video clinic on the General Motors Computer Command Control System. Hopefully, you're more prepared now to diagnose and service vehicles with this popular C3 system when they come to your shop for repair. And we hope to see you again soon on another NAPA Eklund video training program. You can become one of the hundreds of thousands of automotive service professionals who wear the ASE insignia with pride. A symbol that tells your customer and your employer that you've paid the price in study and hard work to master your profession. Whether it's automotive, heavy duty, or auto body and paint. There's a certification program for you. And there's plenty of training available to help you prepare for ASC's written exams. So don't wait. Contact ASC today for more information. There's an ASC insignia waiting for you.